So, which type of bias is preferred, whether it is a preference bias or the restriction bias? A preference bias is more desirable than a restriction bias because it allows the learner to work within a complete hypothesis space that is assured to contain the unknown target function as well, right? So the preference bias is it basically contains a complete hypothesis space, and which is going to assure that it also contains, or it also includes, the unknown target function as well. But in contrast, a restriction bias that strictly limits the set of potential hypotheses is generally less desirable, right? So it basically contains set of potential hypothesis is generally less desirable because it introduces the possibility of excluding the unknown target function altogether. So this is one important aspect of the restriction bias, that is it will have some potentially set of potential hypothesis we are working on, and these hypotheses may include the unknown factors or unknown target functions altogether, right? There are some training data which are not known now, but your hypothesis should also include that as well. But as far as the restriction bias is considered, they may not include the unknown target functions. Okay, so they simply exclude those unknown target functions. That's why preference bias is preferred over the restriction bias. Okay, so why it is, the preference bias is having a very good set of hypothesis space, and also these hypotheses will be sorry they assure you that they also contains the unknown target functions as well. They also contain unknown target functions as well. That is one important aspect of the preference bias. In contrast, a restriction bias that strictly limits the set of potential hypotheses is generally less desirable because these hypothesis spaces may not include the unknown target functions, or in other words, they may exclude unknown target functions altogether. So that is what the inductive bias, that is the preference bias or the restriction bias. So okay, preference bias is preferred over the restriction bias. And there is something called as the outcomes razor. Outcomes razor is the problem solving principle that the simplest solution tend to be the right one. Okay, what that outcomes razor indicates that the for the problem, during the problem solving principle, the simplest solution will be the right one. When presented with competing hypotheses to solve a problem, one should select the solution with the fewest assumptions, right? So you have to choose one solution which is having the fewest assumptions, or the smaller assumptions has to be chosen it. That is the outcomes result. What it says that prefer the simplest hypothesis that fits the data, right? If the hypothesis contains all your training data as well as the unknown target function as well, then you choose that hypothesis. If a hypothesis is able to represent all your training data, or in other words, if a hypothesis is consistent with your training data and also it contains the unknown target function as well, and that is called as the right solution for the given problem. So that is what the outcomes razor indicates. What is that? Outcomes razor is a problem solving principle that states the simplest solution tends to be the right one, right? What it states that the simplest solution, which is going to cover entire training data as well as it also contains the unknown target function as well, it is called as the solution to the given problem. When presented with competing hypotheses to solve a problem, one should select the solution with the fewest assumptions, right? You have to choose the hypothesis which is having the fewest assumptions. In other words, What the Occam razor indicates that prefer the simplest hypothesis that fits the data. Okay, the prefer the one hypothesis which is going to fit all your training data, as well as it also covers the what you call it as the unknown target function. Why prefer the short hypothesis? What is the funda behind preferring or choosing the shorter hypothesis? Argument in fewer shorter hypotheses than longer ones. Why it is? The short hypothesis fits the training data, which are likely less likely to be coincident. Right? It fits the training data which are less likely to be coincident. The longer hypothesis fits the training data might be coincident. Right? You're choosing the shorter hypothesis which contains the training data, which are less likely to be coincident. Right? So they are not coincident, but they are not coincident. Right? And whereas the longer hypothesis fits the training data, that might be the data might be coincident. Many complex hypotheses that fit the current training data but fail to generalize the correctly to subsequent data. That is, for your hypothesis may work for the current training data, but they may not work perfectly for the subsequent data or unknown data as well. Such hypothesis will not be chosen it. So that is how your shorter hypothesis will be preferred over the longer ones. What is that? The fewer short hypothesis than the longer one. Why it is? Short hypothesis fits the training data, which are less likely to be coincident. They may not be the coincident with the training data, but whereas the longer hypothesis fits the training data might be coincident. They might be they might be coincident data. And also the many complex hypothesis that fits the current training data but fail to generalize correctly to the subsequent data. And what is the counter argument with respect to that? That is, they are saying that you are just preferring the shorter hypothesis. That is in favor of the short hypothesis. What is the counter argument here? So there are few small trees, and your prior chance of finding one consistent with an arbitrary set of data is therefore small. The difficulty here is that there are very small set of hypotheses that one can define but understood by fewer learners. Right? So you may represent the shorter, the entire data in a very consistent hypothesis, but these can be understood by very few learners. The size of a hypothesis is determined by the presentation used internally by the learner. Right? So the size of the hypothesis is determined by the representation used internally by the learner. The learner is going to use it internally to construct the hypothesis. Outcome razor will produce two different hypotheses from the same training examples when it is applied by two learners. Right? You will get two different hypotheses for the same training data which is used by two different learners, both justifying their contradictory conclusions by a comparison. On this basis, we might be tempted to reject Occam's razor altogether. From this argument, right, if the same training data is given to two different learners, right, and they may produce two different hypotheses, right, and they may argue that their hypothesis is the correct one. So that is what the counter argument, and with this one they may reject the Occam's razor completely. That is what the shorter hypothesis is all about. Right? Why you are going to choose the shorter hypothesis over the longer hypothesis. Right? There is an argument in favor of the shorter hypothesis, because the shorter hypothesis may be uh, may slightly contains the coincident data, whereas a longer hypothesis may contain the coincident data, and also the smaller hypotheses are able to uh, represent the what you call it as the subsequent data or the unknown data as well. And the counter argument states that if the same training data is given to two different learners, right, or the two programmers, they may produce two different solutions or two different hypotheses, and argue that their uh, argument sorry they may argue that their hypothesis is correct. For this reason, for this contradictory statement conclusions, so we may reject the Occam's razor altogether. And what are the issues with respect to the decision tree? Let us look at there are some issues with respect to the decision tree learning as well. The first one is avoiding overfitting the data, and reduced error pruning rule and the post pruning rule. So, okay, how to avoid the overfitting the data? That is reduced error pruning rule as well as the post pruning rule. And the second issue that arises with respect to the decision tree learning is that incorporating continuous valued attributes, right? So one more issue with respect to the decision tree learning is that incorporating continuous valued attributes. And the third issue with respect to the decision tree learning is alternative measures for selecting the attributes. Alternative measures for selecting the attributes. The first one is about avoiding overfitting of the data. They may be using reduced error pruning rule as well as a post pruning rule. And the second issue with respect to the decision tree learning is incorporating continuous valued attributes. Okay, we are just incorporating continuous valued attributes and alternative measures for selecting the attributes. Okay, what are the measures that has to be taken in selecting the attributes? Handling training examples with missing attribute values, right? So if the training example contains some missing attribute values, what has to be done? Okay, that is one issue with respect to the decision tree. And handling attributes with different cost, right? You have mentioned one cost and you may have inputted some other cost. How to handle those such cost? Okay, so these are the issues with respect to the decision tree learning. The first one is avoiding overfitting the data, and second one is reduced error pruning as well as the post pruning, and incorporating continuous valued attributes, how to include or how to integrate continuous valued attributes, and alternative measures for selecting the attributes. What are the alternative measures for selecting the attributes? Handling training examples with missing attribute values. Okay, what is the handling training examples with the missing training attribute values, and handling attributes with the different cost. So what, how to handle the attributes which are having the differing cost. Okay, differing costs. Okay, so these are the issues with respect to the decision trees. Let us go one by one here. Avoiding overfitting the data. Okay, so what is that avoiding overfitting the data? The ID3 algorithm crosses each branch of the tree just deeply enough to perfectly classify the training examples, but it can lead to difficulties when there is no there is noise in the data, right? ID3 algorithm browses each branch of the tree just deeply enough to perfectly classify the training examples, and it can lead to difficulties when there is noise in the data, or when the number of training examples is too small to produce a representative sample of the true target function. So okay, so it is what it will do is that it is going to create, or it is going to add the nodes, or it is going to perfectly classify the training examples, okay, by just growing the tree or the branch of the tree by just adding the data into it. But if the training data contains some noisy data, okay, if the training data contains some noisy data, then now if the and also when the number of training examples is too small to produce a representative sample of the true target function, then what has to be done? Okay, this whole scenario we call it as the is called as the overfitting of the training examples, right? If you are unable to, if the training data contains the noisy data, and if the training sample is or the training data is very small to produce the representative sample of the true target function, so whole setup we generally call it as the overfitting of the training examples. The definition of the overfitting states that given hypothesis space H, a hypothesis H which belongs to H, that is we are choosing one hypothesis, is said to overfit the training data if there exists some alternative hypothesis H dash which belongs to H such that H has smaller error than H dash over the training examples, but H dash has a smaller error than H over the entire distribution of instances, right? So we'll take two hypotheses from the given set of hypotheses. We call it as H and H dash, which belongs to H itself, right? And in this case, H has smaller error than H dash over the training examples, right? H is having a smaller error compared to H dash, but whereas H dash has a smaller error than H or the entire distribution of the instances. Okay, so this is called as the overfitting of the data, right? We are choosing two hypotheses from a given set of hypotheses, that is called as H. Okay, and H has smaller error than H dash over the training examples. H is having smaller error than H dash over the given training examples, and H dash has a smaller error than H over the entire distribution of instances. Okay, so and this whole concept we call it as the overfitting of the data. And the below figure illustrates the impact of overfitting in a typical application of decision tree learning. So okay, this overall set of states what is the impact of the overfitting on the decision trees. So look at this one. The dotted lines indicates the test data, and the solid lines indicates we are applying the ID3 on the training data. The horizontal axis of this plot indicates the total number of nodes, right, in the decision tree as the tree is being constructed, and the vertical axis indicates the accuracy of predictions made by the tree. So horizontal axis indicates the number of nodes in the given tree, whereas the vertical axis, that is here, it shows us the accuracy of the predictions made by the tree. The solid line shows us the accuracy of the decision tree over the training examples. This is the accuracy of the training examples. The broken lines shows the accuracy measured for an independent set of test examples. Okay, so how the entire tree behaves for a given training data as well as the test data. So in case of the training data, actual training data, the accuracy is very high. The accuracy is very high. Just by looking at the solid lines, you can see that it is having the highest accuracy, whereas for the broken lines or for the test data, it is having the less accuracy rate, right? So it is measured over the a set of independent set of test example. The accuracy of the tree over the training example increases monotonically as the tree is grown, right? The accuracy will grow as the tree grows, your accuracy will goes on increases. The accuracy measured over the independent test example first increases, then decreases, right? From this one, you just look at the things here. For a set of training data, right, the accuracy will always grows with the growth of the tree, right? As the tree grows, the accuracy of the training data will also grows, or accuracy of the hypothesis will also grows. But whereas with respect to the test data, the the accuracy will grow first to some extent, then it will start declining it, or it will start decreasing it. So that is when you are just using the test data. And here is how can it be possible for H to fit the training examples better than H dash, but for it to perform more poorly over the subsequent examples? How to put the training data, or how to put possible for the tree H to fit the training examples better than H dash? That is what the problem here. And overfitting can occur when the training examples contain random errors or the noise, right? It can occur because there are some random errors or the noise. Noise is nothing but the unnecessary inputs, or there is a alteration in the inputs, or there is unwanted symbols have inputted or entered into your data. They are called as the noise or the errors. When small number of examples are associated with the leaf nodes, okay, when small number of examples, or where you have only small number of examples at the root node, in that case you will have the overfitting. So there are some example here for noisy training data. Are these noisy training example: sunny, hot, normal, and the strong. And the last one is not possible, right? So example is noisy because the correct label is plus. The correct label is the plus. Okay, it is an uh, it's a positive example. Previously constructed tree misclassifies it. Actually, this is a positive training example, but as far as the noise is considered, that is, so since the noise has introduced, or noise has been introduced into the data, it classifies it as a negative training example. It classifies it as a negative training example. That is, how can it be possible, right, for tree H to fit the training examples better than H dash? That is how to put the training data examples better than anything else. Okay, and here they have classified the things here. So take one more example here. So 1, 2, 6, 8, 9, they all negative examples, and the remaining are the positive examples. Okay, so there are 14 examples we have it. There are 14 examples, or the training instances we have it. Out of 14 training instances, 5 are negative and the remaining 9 are positive. So you will construct the things here. You will construct the decision tree like this. What is that? If the outlook is sunny and the humidity is high, you're not playing it. If the outlook is sunny and humidity is normal and the temperature is hot, you are not going to play it. And similarly, you just read all the things. But by default, if something happens wrong here in the training examples, if there is a if the noise has been introduced into your training example, if the noise has been introduced into a training example, then instead of considering this particular example, or this particular training example as positive training example, it will be considered as a negative training example. Actually, this is a positive training example. That's why, so this will be classified as negative training example. So your entire decision tree will be wrong. So that's why it is example is noisy because the correct label is plus. It is not a negative training example, but it is a positive training example. But it has been classified as a negative training example that has made an impact on the given decision. And how to avoid the overfitting of the data, okay, in the decision trees. How to avoid overfitting in the case of the decision tree? There are two ways of avoiding the overfitting in the training data, in the decision tree. The first one is a pre-pruning, that is avoidance, and the post-pruning, which is nothing but the recovery. So that is growing the stop growing uh, This way, stop growing the tree earlier before it reaches the point where it perfectly classifies the training data. Okay, stop growing the tree earlier, right? You just try to avoid what you call it as growing the tree itself in the early stages of your construction of the decision tree itself. You try to avoid growth of the decision tree, right? And in the second case, it is the post pruning. So all the allow the tree to overfit the data, then post prune the tree, right? So you just first construct the decision tree, right? Using whatever the data you have, either it is noise data or the erroneous data or whatever the data, you just try to construct the tree and then you record it. Then you could record or you just construct the best decision tree. Okay, there are two methods of avoiding the overfitting. The first one is that pre-pruning, so are also called as avoidance, and the post-pruning, which is called as the recovery. Pre-pruning in the sense that avoidance, which is nothing but stop growing the tree earlier, right? So stop growing the tree earlier, right? You stop it growing before it is too late, right? Before going through all the training example or the training instances, you stop growing the tree before it reaches the point where it perfectly classifies as the training data. And post pruning in the sense that allow the tree to overfit the data and then post prune it, right? You just allow the tree to overfit the data. Okay, you just first construct the tree. So we using whatever the data you have, either it is a noisy data or whatever it may be, then you post prune it. So that is what we call it as a post pruning. And so there are some criteria that is being used to determine the correct final tree size, right? So how to make use of the, or there are some criteria, so they are using it to um, predict the correct final tree size. The first one is use a separate set of examples, that is which is distinct or which is separate from the training examples, to evaluate the utility of post pruning nodes from the tree, right? You just use a separate set of training examples which are completely different from the training examples, actual training examples, to evaluate the utility of post pruning nodes from the tree. So, okay, to evaluate whether the training or whether the tree is correct or not, to evaluate that, you have to make use of training examples which are distinct from the original set of examples. Use all the available data for training, but apply a statistical test to estimate whether expanding a particular node is likely to produce an improvement beyond the training set or not. Right? You just um, use available all the available training data, but apply a statistical test to estimate whether expanding a particular node is likely to produce an improvement beyond the training set or not. An improvement beyond the training set or not. And the next one, use measure of the complexity for encoding the training examples and the decision tree, halting growth of the tree when this encoding size is minimized. This approach is called as the minimum description length, or also called as the MDL, right? Use measure of the complexity for encoding the training examples and the decision tree, halting growth of the tree when this encoding size is minimized, right? You just stop the growth of the tree when this encoding size is minimized. This approach is called as the minimum description length. That is MDL is set to be minimized where it is equal to the size of the tree and the size of misclassification of the tree is, right? Size of the tree, and also plus size of the misclassification of the tree. Using this law, you have to set the minimum description length of the tree. So beyond this tree or beyond this length, your program or your decision tree should not grow. Your decision tree should not grow beyond this MDN. So these are the criteria we are setting it to
avoid overfitting. The first one is that the user separate set of example apart from your training example or the actual training examples. Use a separate set of examples to evaluate the utility of post pruning nodes from the tree. To evaluate the utility of post pruning nodes from the given tree. Use all the available data for training, right? Use all the available data for training, but apply a statistical test to estimate whether expanding a particular node is likely to produce an increment beyond the training set or not, right? Use all the available training data, but apply a statistical test to estimate whether expanding a particular node is likely to produce an increment beyond the training set or not. Here, right, you just make use of all the available data, but before using all the available data, make use of this statistical test to test whether by just including that, by just expanding that, whether we have got the improvement beyond the training set or not. Use measure of the complexity for encoding the training examples and the decision tree, right? That is, you just have to calculate the MDL, that is called as the minimum description length, and that minimum description length halts the growth of the tree. So these are the criteria used to select the to select the correct size of the decision tree. Right. Next one, we'll just go through the first one, that is reduced error pruning. Right. Reduced error pruning is to consider each of the decision nodes in the tree to be candidates for pruning. Right. It is they are considering every decision, every node of the decision tree as a candidate for pruning. Right. And pruning in the sense, a decision node consists of removing the subtree rooted at that node, making it as a leaf node, and assigning it the most common classification of the tree example affiliated with that node. Right? The pruning is with respect to any node is that removing the subtree at that particular node, right? Subtree at that particular node, assigning assigning it the most common classification of the training example affiliated with that particular node, right? So as a reduced error pruning indicates that every node in the decision tree is a candidate for pruning, right? Once it is done, what you are doing is that you are just removing the subtree at that particular node, right? Whatever the subtree attached at that particular node will be removed, and we are assigning it the most common classification of the training examples. We are assigning the most common classification of the training examples affiliated with that particular node. And nodes are removed only if the resulting prune tree performs no worse than the original over the validation set. So nodes will be removed as an like if and only if it performs worse than the original validation set. If it performs worse than the original validation set, then you are just removing that node from the subtree. Reduced error pruning has the effect that all leaf node added due to the coincidental irregularities in the training set is likely to be pruned because these same coincidences are unlikely to occur in the validation set. Okay, that is, you're just removing the nodes. Why it is? Because there is a coincidental irregularities in the training set, right? So you are just removing that node from the tree, since because there is a coincidental irregularities in the list. That's why you're just removing that particular node. So this is what we call it as the reduced error pruning. Reduced error pruning is to consider each of the decision tree nodes in the tree to be candidates for pruning. So they are considering each and every node as the candidates for pruning. And pruning decision node consists of removing the subtree rooted at that node. Right? You are just removing the subtree rooted at that node, making it as a leaf node and assigning it the most common classification of the training examples affiliated with that particular node. And nodes are removed only if the resulting proof tree performs no worse than the original or the validation set. Okay, so if the you're just the nodes are removed only if the resulting proof tree performs no worse than the original or the given validation set. Okay, so the nodes will be removed only when if it performs worse than the original set. If it performs original, sorry, worse than the original for a given validation set, then only you just remove the nodes. Otherwise, you're not going to remove that. And reduced error pruning has the effect that any leaf node added due to coincidental irregularities in the training set is likely to be prone because these same coincidences are unlikely to occur in the validation set. Okay, so because of the coincidental regularities, you're just removing the node because these coincidental regularities will not occur in the validation set. Okay, so this is what the reduced error pruning will do. It the impact of reduced error pruning on the accuracy of the decision tree as illustrated below, right? So in the last example we have seen it. There is one diagram we have seen it. So this is what the diagram or the graphical representation of the data what we have seen it. This is for the set test data, and this is for the training data. So for the training data, accuracy will be monotonous, right? It will increases every time. For every number of nodes you are adding it, the accuracy will increases. Whereas for the test data, for every node you are adding it, it's going to decrease it. The accuracy is going to reduce it. So after applying the pruning, what happens here? Just look at the things here. Just look at the things. The additional line in the figure shows us accuracy over the test examples as the tree is pruned. The accuracy that has been seen after pruning it. After pruning it, when the pruning begins, the tree is at its maximum size, right? It is at the maximum size and lowest accuracy over the test set. Lowest accuracy over the test set. As proceeds, the number of nodes is reduced and the accuracy over the test increases. Sorry. Here, we are just starting applying the errors or the reduced error pruning at this point when it is at its lowest accuracy. When it at its lowest accuracy, we start applying the pruning. Once you start applying the pruning, so as and when the number of nodes decreases, as and when the number of errors nodes decreases, the accuracy will start increasing. It will start increasing it. That is the additional line. That is whatever the additional line we have it, that indicates the improvement in the accuracy as you remove the nodes from the decision tree. Okay, and here is this line is my this line is for my original validation set or the training data, and this is for the test data test data, right? And this is for the accuracy improvement during pruning, right? This is a reverse process here. This is a reverse process, right? As a number of nodes are decreasing, right? As the nodes are removed from the decision tree, right? So you're just getting the good accuracy. You start getting the good accuracy. So the additional line in figure shows accuracy over the test examples. So this is what you will get the training. You will get the best accuracy. When the pruning begins, the tree is at its maximum size and the lowest accuracy over the test set. So you start getting the test set. As pruning proceeds, the number of nodes is reduced and the accuracy over the test set increases. As the number of nodes has been decreased, your accuracy will start increasing it. The available data has been split into three subsets, right? Whatever the available data you have it has been classified into three subsets. One is the training examples, and second one is the validation examples, are used for pruning the tree, and the set of test examples used to provide an unbiased estimate of accuracy over future unseen examples. Okay, so the available data is being classified into three subsets. One is the training examples, and second one is the validation examples used for pruning the data, and a set of test examples used to provide an unbiased estimate of accuracy over future unseen examples. Okay, it is just to these are the three classification, or the entire data is split into three subset. The first set is the training examples, actual training examples, and the second one is the validation examples used for uh, pruning the data, and the set of test examples used to provide an unbiased estimate of accuracy over future unseen examples. The plot shows the accuracy over the training and the test sets. This is the accuracy for the given training data as well as the test data items. And what are the pros cons and of the reduced pruning? The first one, pros or the advantage of the reduced error pruning is that produce the smallest version of most accurate tree. That is a subtree of the tree. It's going to give you a smallest version of most accurate tree. That is a subtree of tree. But there are disadvantages with respect to reduced error pruning. Pruning here. First one, uses less data to construct. That is, compared to the actual training data, it is going to use less data. It's going to use less data. Can afford to hold out devaluation. If not, data is too limited. May make error worse. That is insufficient. That is a training, right? So since you're just making use of less data to construct the same decision tree, it will make the like you don't have the good result, or you don't have the better decision tree. So this is what the pros and cons of the decision tree. So the process are that uh, the pros and cons is that it produces smallest version of the most accurate tree, right? You are having most accurate most accurate the tree decision tree for the it is the smallest version. And but the problem with the reduced error pruning is that it is just making use of the less data. It's going to make use of the less data. These are the two, the pros